Okay. So up until now we have been talking about submodular maximization, submodular minimization, or whatever kind of thing. Today we will talk. Hopefully, this is the last lecture on submodular maximization. Okay, and what are we trying to show is the following. Let's see. We'll try to get an approximation, some approximation for non-monotone non-monotone submodular maximization, okay, and that also with the cardinality constraint. And we are doing streaming setting. Okay, so let's see what are we able to guarantee, what are we able to give, and so here's an algorithm. Okay, so up until now, notice that whenever we have tried to make an algorithm for non-negative, non-monotone submodular maximization, then we try to, in some sense, capture two sets and try to output solution which are in some sense best of these two worlds. Okay, so we will have to somehow do this process in the randomized setting and or in the online setting or in the streaming setting or whatever you want to say, and somehow able to say that whatever is happening is nice. Okay, so okay, so algorithm is as follows. So we will assume that z is given to us, which is between guess, like assume we have guess the value of z, which is between opt and 1 plus epsilon opt. Otherwise, we can do this in parallel by running, right? 1 plus epsilon to the power 0, 1 plus epsilon to the power 1, 1 plus epsilon to the power square, and so on and so forth. Okay. So now we are going to maintain two set. S1 is going to be phi, and B, another set, is going to be phi. Okay. Now, for each element in the stream, right? For each element E in the stream, okay? What I'm going to check, I'm going to check that what is its marginal contribution if I add this element to S1, okay? So I check if mod S1 is less than equal to K, okay, and f of E S1 is, so like, is greater than or equal to, we will fix something, okay, then B is B union E. So if this is greater than some threshold, then like if I add this element S1, then I add this, okay. Look, up until now I haven't added anything to S1, okay. Now I see if mod B is less than or equal to K epsilon, okay, or not less than, equal to K over epsilon, or this also will fix, okay. So let's fix this threshold as x, okay, we'll fix some threshold x, okay. So remove a random element from B and add it to S1. So this is what I do in this step. First, so if cardinal, so till I can add many elements of B, right, I add it. So remember, this is exactly like, so what am I trying to add? I don't know, so if you look, what was the non-monotone cardinality version? We said pick the B of k elements which maximizes the total, which maximizes the f summation f si. So this B is just going to act like this. So whenever adding a marginal contribution is large, I am sending that element to B, and if B becomes large enough, I remove a random. And what is the property of first time when you do this? Is that everybody in B has marginal contribution at least x compared to current S1. So any element can be added, and at least by value x, its marginal will increase. But when I removed a random element from B and add it to S1, now if I add the current set of element from B, that marginal may not increase, right? So what should we do? We should throw away those elements, okay? So this is remove any element from G. So B is your buffer of elements whose, like if you add any element of those to the current S1 which you are trying to maintain, then you can, then you are guaranteed that marginal will increase compared to that set, which is good, okay. So for example, if I was looking for approximation algorithm, say beta, okay, then I would substitute here, say beta into z, and then say add it to x, remove a random element, remove any element from beta z. So if I am looking for the factor beta approximation, I will say beta z over k. I will tell you why in a minute. So remove any element from any element G from B such that adding to S1, okay, adding this element, what am I saying? Wait, for some reason I wanted to stick to a slightly different notation. Okay, so I will, let's stick to this notation, okay, for some reason. It will be slightly easier for us to understand. All notations are same. Okay, is less than equal, strictly less than beta z over k, okay, then remove any element G from B such that this happens. So now I only want to maintain elements in B whose addition to S1 gives me lot of value, additional value, okay. So that is what. So if I add in an element, I know its function is not monotone or something. If I add any other element, the value could decrease. So I have just deleted those elements, right? This is why I do this. This step is to clean up this process so that I'm guaranteed. So whenever I add element to S1, I'm guaranteed that the marginal contribution of adding this element to S1 is large enough, right? It at least this much, whatever that quantity is, okay? Now we will do some post-processing. Okay, so what is post-processing? S, which we are going to return, is maximum of argmax f of z. Z is element of S1 comma S2. So S1, you know what S1 is, where S2 is the best solution from B. Okay, so look, this step is not polynomial. It depends on the size of B, because I will try all possible subsets at potential S2. But that's okay. It's all about storage. Okay. Now, what is the space complexity of this algorithm? Right? All we are going to do is going to maintain some S1 and B. Right? And how many elements are we going to maintain in S1? S1, we are going to maintain some, so space will be like O tilde, because we'll do some log n m steps here to guess the correct Z, right? And you're just maintaining some k elements here and some k elements here, right? And some tests. So something like number of elements is like order k, O tilde k. That's it. That is the space taken by this algorithm. right? I'm only going to store, and I'm never going to store more than, look, this step only happens when this is less than k. This step happens, and at the end, total number of elements stored is like k plus k by epsilon. So like some order k elements are stored. Okay, so space is not an issue. It's a very efficient algorithm. What is absolutely not clear is that, I mean, even given that we try to deduce some sort of intuition from our maximization algorithm from non-streaming setting, it is not clear the same way, even for the monotone thing, it was not clear to us that anything happens when an element is added later, right? Why will such an element exist at all is also not clear to us. Okay. Okay. So first of all, here's a small lemma. Okay. And what this tells us, if mod s equal to k, then f of s1 is at least beta z, okay, and which is beta times opt. Okay, by our choice of z, right? I want to prove this. Okay, proof is very simple for this, right? Because this is exactly what we have seen proof. So let s equal to a1, a2, dot 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 ak in the order of their inclusion in S1. What are they guaranteed at each step? That whenever so suppose I have added ai, when I add ai plus 1, they add beta z by k, marginals. So whenever each time your marginals increases, you can just sum them like this thing, because otherwise you can do this curly summation, right? So what is f of s? F of s is summation I equal to 1 to k, f of a1 to ai, right? F of a1 to ai minus 1, right? We can do this sum. This is exactly what, is this f of s? Can I say this? Yeah, this is fine, right? This is what I can write f of s. Is this correct? Let's see. So what will be this? What is this? So everything will get term, but I think what will be left is f of s minus f of empty set. This is what will be left at the end. So this is actually, so I can say this, f of s minus f of empty set is this. This I can say. And now each of this entry is at least beta z by k, right? Right? So what will you get? K times beta z by k. So k will cancel. This is at least beta z. So f of s is at least beta times z plus f of empty set. But this is non-negative function. So this is at least beta times z, which is at least beta times opt. Right? So definitely, whatever beta approximation algorithm I want, I can substitute it here. So this is not our limiting factor. Limiting factor will be the other case when, so this is like very, like I can put 1 for all that I care. Then I will get, so if I get 1, then I get optimum solution in this case. Okay. So now, so the hard case is, okay, so this is one lemma which we wrote. Let's write the second lemma. If mod s is less than equal to k, strictly less than k, then what can we say? Then for the optimum set O is an optimum solution, okay? What can we say? We can say f S1 union O is less than equal to f of S1 plus f of O intersection B plus Z by 3. Okay? Okay. So first let's try to get some lower upper bound and let's see what all things we need. Look at this term f of S1 union U. What is this term? This term is nothing but okay. What is okay? So let's see. Let's write it here. What is f of O S1? Let's not write this way. What is f of S1 O? It's nothing but f of S1 union O minus f of S1, right? So I can write it f of S1 union O is f of S1 plus f of S1 times O. Okay? Okay. Now notice, look at this function f of S1. This function f of S1 okay. Okay. So now notice that f of S1, which is a function I defined from 2 to the power n to r positive. What is this? F of S1 of x is f of x union S1 is also non-negative submodular function. We can prove this. We have given this argument several times. Okay. Now, so I want, in some sense, so look, I want an upper bound on f S1 union O, right? So I know that this is equal to this plus this. So this I have anyway here. Somehow I have to be able to get this term upper bounded by these two terms, and then we will be happy. Okay. So now what I'm saying, okay, so we also know by some modularity that f of A plus f of B is greater than or equal to f of A union B plus f of A intersection B for any set A and B. So now I'm going to take A as O minus B okay, A tilde, B tilde, A tilde, B tilde, A tilde, B tilde. So O minus B, and what is B tilde? I'm going to take O intersection B. So basically I have written O in two ways. Like this is basically, if you look at O and B, this is what? O minus B, and what is this? O intersection B. This is what it is. So now if I write this, what will we get? F of f S1 of O minus B, this is what we get. I apply to f of S1 function, plus what is f of B tilde? F S1 O intersection B, right? This is equal to f of S1 of O plus f of S1 of empty set, which is equal to f of S1 O plus f of S1. 1. Okay? Okay. So now what is f of S1O? Okay, so this is at least f of S1O, this quantity, because this is positive quantity, right? So I can write f of S1 is lower bounded by this. Okay, so now I can go and substitute here. So then I will get here f of S1 remains f of S1 plus f of S1O is upper bounded by these two terms. F S1 O minus B plus F S1 O intersection B. Okay. Now let's try to get some sort of upper bound on this. Okay. So let's try to see what this is happening. Okay. They have some other, this is like, okay. So let's just keep here 1, okay. Now we are just trying to get an appropriate upper bound on each of these terms and replace it with this, okay. Now let's first try to get an upper bound on this term, okay. Okay. So, okay. So now what I'm going to do, let's try to look at, let O, so I can say this for any element. For each element O in O minus B, I want to say something, okay. For each element O in O minus B, I want to say that, look, f of S1 O is, I want to say this is like less than equal to beta z. How do I say this? Look, O is in O minus B, right? So what is this? So definitely O does not belong to S1 and B, because O never belonged to B, or maybe B from this would have been thrown out from it. It was something good, but okay. So when we are going to consider O, look at the time when we are considering O. Look, why O does not belong to B currently? Either when you were taking O here, right, here, this failed, or after adding an element this failed. Either way, let SO be subset of S1 when O was considered and thrown out, considered and removed or let go, right? At that point of time, why did you let it go? Either this condition is not satisfied or this condition is not satisfied. Either way, we can say at this point of time that f SO O is less than equal to beta times Z by K. Agreed? I can say this for sure. Now, what do you know about S0? SO is contained inside S1. So now, by the marginals of subset contained inside a subgraph, what we can say? We can definitely say, look, if adding O to S1 is less than adding O to SO, because SO is contained inside S1, right? And that is equal to beta Z by K. So that is why it is got beta Z by K, right? So just consider at that point of time when you have, like, look at the status of SO when you were throwing out O or you are letting O go, what is its marginal with respect to that? Now in future you can only add elements to S1, right? So SO is contained inside this, and then by the principle of marginals of subsets, this you will get, okay? But this is not, but what we are interested in, so for each element O this is true, but what are we interested in? We are interested in f of this quantity. Okay, what we would like to bound this with? We would like to bound this with beta z, right? So basically we want to say, look at f S1 O minus B. I want to say this is less than equal to beta times z, because at most there are k elements, so k times this, okay? So this is what I would like to say at this point of time. So I'm just going to rub this, but look, I can probably apply this kind of argument just to add here, right? Why? Because look, now suppose I can write, okay, so let's try to just get this off, okay? Suppose O minus B1 is O1, O2, OL, okay? Okay. In the, I don't have to say anything here, okay? Okay, let's see what are we able to get it. So this is how it is. I'm going to add S1 union OI S union this. So what is this? This is, what will we get from here? Right? So what are we going to get from here? We are going to get here, what is this term from here? It is just going to be f of S1. Phi is going to be S1 because this is this. And what is the last term? It's going to be S union O. Because O minus B is 1. No. This is not what it is going to be, no? I should not write O minus B, O minus S1. We did this. So now what will we get here? F of O union S1. Right? And what is this then? What is this term? This is nothing but F S1. This is something wrong, no? Maybe. If I do O minus B, yeah, I only needed S1 O minus B, right? So why do I need to do this? So f of S1 union O minus B, right? Minus f of S1, which is same as writing this is equal to M1 O minus B. Okay. Now what do you know about these two terms? This minus this? Can we say anything? Okay. We have to be careful, no? Because, one second. So this is less than equal to summation I equal to 1 to k. Look, these are definitely contained inside a single element which they represent. So suppose OI is contained inside there. What is this? What can I write this? I can write this as f of S1 of, let's call it OI is O1 to OI. Can I write this? This is what it is. Now each of these term summation I equal to 1 to k is less than equal to f of s1 little o of I. Because look, here is your s1, S1 union? Oh, I didn't get your point.
First summation.
Mm-hmm.
F of S1 union OI to OI minus 1.
OI to?
The subscript.
Okay.
So S1 union OI to OI.
Right. This is what it is. Minus 1
OI.
little oy, right? This is what it is. Okay. And then it is easy to see this. But this is less than equal to, we have shown this is less than equal to, right? For any O this is true. What happened? Huh? Beta z by k times k, because O minus b is at most k. Okay. So what did we manage to show? That this is definitely less than equal to beta z. Okay. This term. Okay. So notice one thing, that all the time it boils down to coming up with right selection of O's and this and writing as a marginals. This is it, right? And then you will be able to. But from here to here, how will we go? There should be a way to go from here to here. I really don't know, but let's see. Okay. So the key idea was this, and now by now we should get used to this kind of argument, like writing it as a marginals and this and that. Okay. So now, so we have been able to show this term, this is less than equal to f of s1 plus beta z plus f of s1 O intersection b. And now we need to show somehow that even without s1, this is less. This is what this term is, right? Need to show let's see. Do you have any argument for this? There should be something easy happening here. So what we need to show? We need to show okay. So what is O intersection B? Is this? I think we can similarly write this also. Because what is happening to O intersection B, we are keep on adding elements, right? So, and here is your S1. So basically what are we saying? Yeah. Oh no, come again, what are you saying?
If S1 of O intersection B equals F of O intersection B
Minus what?
union S1 minus F of S1, right?
Why? Okay. Minus f of? Okay, fine. Yes?
This is upper bounded by F of O intersection B union S1.
This is upper bounded by f of O intersection B union S1. Okay, sure. Yeah, this is fine. Hmm? We already threw in submodularity to get there. How did we get here? By throwing submodularity. I have no clue why this happens. So for now, let's just believe that this happens. Okay. Look, it must be some other stupidity of submodularity here and there. It is just it is not some brain. So let's not waste our time on that aspect. So okay. So this is an exercise. If someone can get me, do you have any solution? Yes, Abhishek, tell me. Should I rub this? Okay. Okay, tell me.
You are adding O intersection B to S1.
Yes.
Then look at their marginal contribution.
This is what I was. So you want to look at.
Just look at two sets S1 and empty set.
S1 and empty set. Fine.
So in the first case, you are adding O intersection B to S1.
O.
You are looking at their marginal contribution.
Yes.
And in the second case, to phi you are adding this O intersection.
Yes.
So for the phi case, this value will be larger. Since phi.
We should either prove it that it is true about any number of elements added. Either we should prove that as a lemma somehow, right? That what I mean by this. Look. So what are we saying? So we have set x and set y, right? And then we proved for element E, f of x union E minus f of x is greater than equal to blah, right? Maybe we should also prove this for set W. And maybe this is true. But what are you trying to apply? Think for a minute. You are saying, hey, let's look at empty and look at S1, right? I added one element to this. Then clearly this minus f empty is greater than equal to this f S1 union this minus f of S1. Am I right? But O intersection B could have several elements, which is same as proving the following element. Okay, so let's see if this is true. It should be true. Okay, so what I'm saying is that what is that wrong?
You can always keep adding these elements. For one addition of one element, if it's true, then you can.
So let's prove that. This is exactly what I'm saying, right? Rather than believing in whatever you are saying, okay, like let's prove a lemma, right? Then we can invoke this lemma all the time, right? So this is all that I'm saying, that let x be subset of y and O be subset of n or z be subset of n minus y, then what is that called? Then f of x union z minus f of x is greater than equal to f of y union z minus f of y. Is this not what we want to do? Okay. So for the proof, probably what we'd like to do is like let E1, E2, EL be element of n minus y. Okay. And what we would like to show, yeah, so let's do summation f y union E1 to EI f of y union, right, I going from 1 to L, right. So this is less than equal to summation I equal to 1 to L, what is that called, f of x union to E1 to EY because we are applying single element operation with uh, with single element operation with x E1 to EI minus 1 and y like this. Okay, so this is fine. Okay. Now, what is this less than equal to? Now this will get cancelled all the intermediate term except what will be left with? What will be left with? The first term, which is minus f of x, right? And the last term, which is f of x union z. This is z. Okay, fine. Okay, excellent. So this is, now we have this lemma. It's not only one element addition, but you add, if we have a subset, and add as many elements as you like. It doesn't matter. If you are adding the same set of elements to both, the marginal of adding that big set is going to be intuit. We have been doing this several times, so that's okay. So then now we are happy because how will we show this as pointed out by Abhishek is that let's take empty set and let's take S1 and you have O intersection B is outside. Okay. Now if you apply to this, what do we know? We know that f of O intersection B minus f of empty set, right, is greater than equal to f of S1 union O intersection B minus f of S1, which implies that this is what it is less than equal to f of O minus B minus f of empty set, which is less than equal to f of O intersection B, because this is positive. Okay, so we managed to show this quantity. Okay. Excellent. Thank you. So for the proof, now we need to bound this, right? What is the approximation factor, ratio, and all those kind of things. Okay. So for the case when mod S equal to K, what did we prove? Mod S1, f of S is at least beta Z, which is beta times opt. This we already proved. Okay. So the only case we are worried about is this case. So what is this case? So in this case, okay, so now mod S is less than equal to K, and from here we can say f of S1 union O is less than equal to f of S1 plus f of O intersection B plus beta times Z. This we proved. Okay. Okay. What can we say about f of S2? I claim that f of S2 is at least f of O intersection B. Why? Because what is your S? S is maximum of S1 and S2, where S2 is the best solution from B, and O intersection B is contained inside B. right? Okay. So it means I can write f of s union O, right, is like less than equal to f of s plus f of s plus beta z. Because S1 is also less than f of s, right? F of O intersection B is also less than f of s, where f of s, where s is the best of these two solutions, right? So first you show that S2 is better than f of O intersection B because S2 you're going over all subsets of B and taking the best solution. So in particular you're going to consider O intersection B. Okay. So this is equal to 2 times f of s plus beta z. So notice one thing, up until now, only one place we have used randomization. What is the randomization we have used? When we are removing a random element. So from surplus, we are adding an element from B to our S1. That is the only time when we are going to add, what is it called? We are going to apply randomization. This is here. Okay. So what is the probability that an element from B never gets added to A? Or rather, what is the probability? Let's ask ourselves a question. What is the probability that an element from B, okay, does not get added to S1? Let's ask this question. What is the chance that, so fix some element. It might not have been, look, it might get not added in the first chance, right? It might, or it might got thrown away second time, then I don't have to worry about, right? So probability that an element from B does not get added to S1 is at least or at most. Okay. So first of all, it doesn't get added in the first round. What is the probability that it does not get added? So let's write K epsilon. What did I write? What is the size of B? K by epsilon divided by random element from B. So what am I writing here? Remove a random element from B and add it to S1. Okay. So you are not adding it to him. Is this? Which is what? 1 over epsilon by K. Right? Okay. Now, it is not added in the first round. It is not. So, what is the probability that element from phi does not get added to S1 is at least this much. At least this much. It may be more, but it is never more than, it is never less than this. Why? Because look, its probability will be like 1 minus epsilon by K if it does not get added in the first round. If it does not get added in the second round and thrown out, then its probability remains this, which is larger than this number. So more and more round it doesn't get added, probability only dissipates, it doesn't increase. So this is what happens. So probability that an element from B doesn't get added to S1 is upper bounded by this. So probability that an element from S1, from B gets added to S1 is at most how much? 1 minus epsilon by K to the power K. Right? This quantity. Okay, now we had this nice lemma from last time which said the following. Do you remember this probability lemma? No? Okay, so this is the lemma which we proved last time. Okay, so what did we prove last time? And we also used this lemma last time. So this is the lemma which we proved. What is the lemma we proved? Let f be a submodular function denote by AP a random subset of A, okay, be a random subset of A where all elements appear in A with probability at most P, okay, with probability at most P, not necessarily independent. Okay, not necessarily independent. Then what did we show? Then we said expectation of f of AP, right? Expectation of f of AP, okay, is at least 1 minus p times f of phi, right? This is what we proved. So now look at S1. S1 is constructed in a random way from some subset pool of elements. Think of that as your B, right? Where any element gets added to S1 is upper bounded by this probability P, right? And so I'm going to apply, I shouldn't be saying, yeah. Where is my, okay. So this is what I want to throw now, right? This is what it is, okay. So what is so now I want to apply this lemma here, right? So if I can get a lower bound on what is an expected value of S1, then I definitely get a lower bound on expected value of S, because S is maximum of these two quantities, right? So this is what we would like to do now by throwing up this lemma. And we prove this using, if you recall correctly, like we take the decreasing order of probability and we added stuff and things like that. So we already proved it. So what does this technical lemma yields us? This technical lemma, so now I want to apply expectation over this function. So if I apply expectation over this, what do I get? Okay. Applying expectation both sides of B, we get, what do we get? Let's write it down. We will get expectation of f, or expected value of f of s, is at least expected value of f is union O, right, divided by 2 right, and this is fixed quantity, right, minus beta by 2 z, right. I just took that quantity, I moved everything other side and divided by 2, so it will come out like this. Now I want to get a lower bound. I want to get a lower bound on this quantity using this formula. Okay. Okay. So let's see. what are we able to get it? Okay. So what is an expectation of F S1 union O? Is at least the probability, which is this quantity. So it is 1 minus P. So 1 minus this get cancelled, this is a plus. So we will get 1 minus epsilon by k to the power k f of O. And what is this quantity? What is this quantity? What is this? I can write this as k over epsilon times epsilon, right? So what will we get? What will we get? F of O is opt, so this is what I substituted the value. What is this? What is 1 minus x to the power x is at least 1 minus x, or right? Yeah. No, this is not true. What is this? Wait. Can I say this is greater than or equal to 1 minus epsilon? Or what is this? What is this quantity? What is this? That's a lower bound. Wait. There are also like 1 minus x. Okay. Is there not something like 1 minus x? Can I say this? Can I say this? Let's see. Wait. I mean, look, you people do not understand. This quantity is okay, let's write it down separately. 1 minus 1 over, I can write it that as ky epsilon to the power k f of O. It's the same thing. Okay. Now, we can show this quantity. So 1 minus 1 by x to the power x, 1 minus 1 by x to the power x is, or let's say y, is greater than or equal to 1 minus y by x. Do you want me to prove this? Okay, I'm not going to prove this, but you can show this. Okay, so if this is what it is, then what will we get from here? I'm using this inequality. There could be some x, y should be positive or something. Yeah, x, y is greater than 0. So now what do we get from here? K which is 1 minus epsilon times f of O. Okay? So what will we get now if I substitute there? We will get in C, we will get what? Expectation of f of s is at least one minus epsilon f of O by 2 minus beta by 2 times z. So I am writing lower bound. So what was z is 1 plus epsilon time opt. Right? So let's write it here opt, and here I can also write 1 plus epsilon times opt, right? Because I'm subtracting the larger quantity. So this is equal to, if I take opt by 2 common, what will I get? If I take opt by 2 common, what do I get? 1 minus epsilon minus beta. Is this correct? So we get this to be opt equal to, okay, so actually I can take 1 minus epsilon common. Then what will we get? Can we take 1 minus epsilon common? No, we cannot take. I think we can take 1 minus beta, plus, is this correct? No, 1 plus epsilon, right? 1 minus beta I wrote here, and I take minus epsilon common, then what do we get? 1 plus beta. Is that correct? If I take 1 minus beta, I take minus epsilon common, so minus epsilon, and then minus 1 plus beta, right, by 2. This is what it is. Okay. Now I want to look, epsilon is in my hand, but beta I could choose, right? I have to choose beta that both sides are maximized, like equal, right? So I should try to optimize this value when, so in one case we get what? We get beta z as an approximation algorithm, right? Beta times opt. So if I want to optimize, look, if I take beta 1, what happens here? If I take beta equal to 1, this guy goes to 0. And what do you get? Look, you get nothing, because then you get negative quantity. So you need to choose beta in a way that this is positive quantity first of all, and I should try to make it equal to just beta. Okay? So let's try to see if we can do some such computation. Right? We have this beta times opt, and the other case we have 1 minus beta minus epsilon 1 plus beta by 2 times opt. I want this to be as good as possible. So it means 1 minus beta minus epsilon times 1 plus beta should be equal to 2 times beta, which is, and now we are trying to solve with respect to beta, right? What approximation factor do we get? So what is this? 1 minus beta minus epsilon beta. So this is equal to 3 beta. right? So if I take epsilon this side also, so what will be the factor of approximation? 3 beta plus epsilon beta should be equal to 1 minus epsilon, right? So beta should be 1 minus epsilon 3 plus epsilon, right? So basically beta is like 1/3 minus epsilon. So if you choose 1/3, you can get 1/3 minus epsilon approximation by choosing epsilon prime, which is smaller than this. So this is what you will get. Okay. So this is what we achieve for what is that called? For submodular maximization. So we did two kinds of submodular maximization. Okay. So let me give you some more. So for here, how much was the space complexity? So if you recall correctly, we did monotone also streaming, right? And that was also taking us how much? We were just making some guess jade and we did this. But so how much space did it take with respect to k? So that was also that was factor half approximation we gave, right? So what? So let's summarize what all things we learned here, okay? And let's see what next we can do. Okay. So we made a long tour. Okay, we made a long tour and we learned first unique coverage. What was an approximation? 1 minus 1 over E. Then we learned set cover ln n plus 1 and ln d plus 1 approximation factor algorithm. Okay, so this is the two things which we learned first, and then like non-streaming setting. Okay, then we learned what submodular functions were, and then we did submodular maximization, monotone cardinality constraint. And here also greedy gave us how much? 1 minus 1 by E in what do you call? In non-streaming setting. Right? And then we did monotone cardinality greedy, but we got half minus epsilon approximation in streaming. Right? And what was that algorithm was very simple actually. What we did there, if you recall correctly, we guessed Z, right? And in the beginning we had A equal to empty set, and for every A, okay, for each U in U, what we did, if adding Z if it was more than z over 2k and mod A was less than equal to k, we added z in U2A. This was a simple algorithm which we gave was half minus epsilon. So here also if you notice, it never stores more than O tilde k elements, right? So this is what we learned. And then we went to submodular maximization, non-monotone, but non-negative, non-monotone, non-negative. Okay. Okay. So okay. So this is what we did, non-negative. So here we did two versions. One was unconstrained, and here we gave randomized 1/4 approximation, and we got this probability lemma starting from there. It got attached to us, and we give two analysis. And then we gave a deterministic 1/3 approximation. Okay, and we discussed a little bit how to get it to half by making the probability proportional to like which side gives how much. And then we had cardinality constraint, cardinality constraint. And what it was, 1 over E, approximation again randomize. Okay. Okay, submodular, unconstrained, cardinality constraint. And finally, today we saw in the streaming setting, one-third minus epsilon approximation. Okay. Now imagine yourself that we wanted to do, so all these things are fine, okay? If I wanted to do, say, max coverage, right? Which is same as, it was not unique coverage, it was max coverage, right? If I just wanted to do max coverage, I could run one of these, because that is a submodular function, I could run one of these algorithms, but how much space will that take? Let's try to understand that. You are going to store whole how much space will take? Look, there is also some epsilon here, which I always hide. Okay? How much space will it take? So, what are you going to do? Now, what is going to come? Sets are going to come. What are going to come? Sets are going to come. You will add that set to your current solution if the marginal of adding this set is large, which is basically the number of uncovered elements, right? If the number of uncovered element is larger than some fraction, like if it is larger than z by 2k, then you will add. But then what is the space taken? It will not depend on just k. A space taken will just not depend on k. Because look, I am keeping whole sets. So now space will start to depend on m or n. It will not only depend on this, right? But there is a way to do subsampling, which can reduce the space for maximum coverage to order k space. Okay, there is a way to do subsample and do things. Okay, this is one. And this we will see, maybe not today, is dominating set. Okay, so what could be a trivial? So first of all, suppose I wanted to do dominating set, or rather than saying dominating set, let's say set cover. First of all, we shouldn't be able to do better than log n approximation in a static setting, but maybe we can, because all we are trying to tell us that if we can say that, look, in poly time I can save small number of space, then like I can store all the optimum, because here time is not a constraint. So we could improve the approximation factor. Right? But if we maintain that everything is done in polynomial time, of course we cannot solve. Okay. So here I use crucially here, if you notice, for the last one, that look, all I care is about space, I don't care about time. But if I start to care about time, the algorithm which we gave for 1/3 minus epsilon will not work. We will have to tweak that algorithm accordingly to make it work for. So there are multi-passes algorithm for this, and this we will see. Passes algorithm for set cover. What I mean by multi-passes algorithm? So each time sets will be coming, and we will be like not once but several passes will be happening, and we will be covering these guys. Okay. So I think the most obvious algorithm is, let's see, or a simple algorithm. This is also a, let's see. So we will do a slightly much more clever algorithm using random sampling. But let's say I want to give you a p pass, okay, a p pass O tilde n space algorithm. So here is universe has size n and family has size m. Okay. So O n space algorithm returning, so a p pass O tilde n space algorithm returning a p n 1 over p approximation for the minimum set cover. Okay, let's substitute p equal to 2. What are we saying? We can give a 2-pass algorithm which takes how much space? O tilde n space, but what will this approximation factor? This, right? So do you think you can come up with such an algorithm? So what are coming? Sets are coming. So let's try to do it for 2. For 2. Look, how much space do I have? O tilde n space. So I can certainly have a bit vector which tells us whether an element, particular element is covered or not covered. Okay. So I can have covered, uncovered. Right? Right? So that's it. And I can, after one pass, I can definitely go get all the elements if I wish to have. Look, at the end of one pass, I can get all the elements. For example, if all my objective was to get the universe, I let all the elements go and I put them in uncovered, uncovered, uncovered. If new element comes, I just put it in uncovered. So at the end of this process, first pass, I know my universe. I'm not storing sets. I'm just storing my universe. Okay, but I don't have to do it. I can do it on the fly. Okay. So what I do, let's try to understand. At any, so now sets are coming. Okay, sets are coming, and if a set covers at least 2 root n new elements, add to our solution. Or not add to our solution. If a set covers new elements, add to the uh, add to our family f tilde that we are trying to maintain. But how will, so look, if I store whole set, I mean, so what happens in the after the first round? After first round, you would have covered some x number of elements, right? So suppose in round 1, right? So I just keep adding covered, and if I decide not to add, I put them in uncovered. So in first round, I have taken some sets, okay? So round 1, after round 1, what is the property of any sets which are not taken? How many elements can they pick up from uncovered? Look, when they were opportunity, right? When they had an opportunity, right? I have some threshold. I know what elements are covered, right? So I just counted all the uncovered elements it had, right? It is strictly less than 2 rated. Later, I might have added those elements because of some other set. But after round 1, no set can cover, or every set covers strictly root and 2 rated new elements. So in the first time, I have covered x elements. Okay. Suppose I took, in the round 1, I took x sets. It means I have covered at least 2x root n elements. Right? 2 root n x element. So number of elements that I will take in the second round, let's try to understand how much element will I take in the second round. Let's see. In the second set, suppose in second pass I take all uncovered sets. Like for every element I just pick up one. Right? We will do something much more smarter, but for now, for every set, for every uncovered element, just pick a set. For every uncovered element, pick a set. Let's try to understand what is the approximation ratio and how much is the space taken. Look, even if I take root n sets and store them physically, I'm going to take n root n space. Then what do they mean by O tilde n space? Okay. So what do they mean? You don't remember the set, you remember the ID of the set. Okay. So you just 10th set, 15th set, every set has a number. Okay. So what you store, so this is a model. I mean, this is not something which, so I just remember, I'll tell you, like there exists a solution consisting of 10 sets, 15 sets, 20 sets, 25th set. I not store the physically the set. Otherwise it's impossible to get such kind of algorithm. So this is something to remember. Okay. So you output or you store ID of sets that you want to select. clearly I will never select more than n IDs, because I mean, why will I like to have more than n sets into my solution? Because all they have to cover is n elements. Okay, so this is why this is taken care of. Now, with respect to approximation factor, look here. Look at the first. I at least cover 2x root n elements. Each set covered 2x root n element. It means, how many sets did I take? Let's try to understand. I took x sets plus for every, I took n minus 2x root n sets. This much at most. Number of sets picked is at most this much. Do you agree? Okay. What does this imply? Can I get a lower bound on opt? Look, lower bound on opt is, first of all, x is less than equal to root n by 2. Because every time it covers 2 root n new elements, there are only n new elements. Okay, so x is upper bounded by root n by 2, right? Fine. So total number of sets that we have taken is root n by 2 plus, look, I took all the big sets, right? Whatever maybe the remaining guys are here, right? That is like the opt is at least n minus 2x root n by root n. Because every guy can only cover root n elements. So how much, I mean, I shouldn't say this way, like, or maybe the best way is that number of elements covered is like y, and so for every element, so number of sets you picked up, it's some x plus n minus y, right? So the number of sets you picked up is x plus n minus y. So root n by 2, and opt you definitely know is at least n minus y by 2 root n, right? So if you do computation using this, you will get that this is like a root n approximation. Okay, so this is the way to get a root n approximation, and this is not something very hard, but this is like just to give you a feeling that why are we getting these kind of bounds here? It is because of this. Okay, now let me give you the really algorithm itself. This is called, so you still maintain covered, uncovered, right? And let's do the analysis. So this is called algorithm with decreasing threshold. Okay, so first you take root n elements, then you will take n 1/4 elements, n 1/8, and this, right? So algorithm with decreasing threshold. So we still have maintaining covered, uncovered. So what is our algorithm? This is called decreasing threshold. Okay, so this is our algorithm for decreasing threshold, which is very simple. This is just one line algorithm. For I equal to 1 to, for I equal to 1 to log alpha n, where alpha will be something fixed, where alpha is n to the power 1p. Okay, in pass I, add all sets. Okay, add all set or add any set that cover how many? Heart that covers more than n to the power what? Alpha to the power I new elements. That's it. This is my end of my algorithm. Right? So in each pass, I decrease the amount of threshold. So suppose I wanted n to the power 1/3 approximation algorithm, p is 1/3, right? So then what are we doing in the first round? Let's put p equal to 3. So first round, what I'm saying, let's take n to the power, what is this? Alpha is n to the power 1/3. So n to the power 1/3. Next time, n to the power 2/3. And next time is n by n. Right? So this is like n to the 2/3, n to the 1/3, and 1. Right? So if you had 4, then you would have n to the power 3/4, right? N to the power half, n to the power half, 1/4, and then 1. Right? So this is how we are going to add elements to our set. So let's do first space and pass analysis. Okay. As I explained to space, we are never going to keep more than n IDs of sets, right? So that is space is definitely order n, okay? And now how will we get pass? Setting alpha equal to n to the power 1p, what does it gives you? It gives you that you cannot have more than p passes actually, right? Because in the pth pass, you take any element, any set that covers one new element, and like that's perfectly fine, right? Okay, and setting alpha equal to n to the power 1 by p gives us setting alpha to n to the power 1 to the power p gives us p passes. And here's an exercise for you people, okay? This is really exercise. Combine last two steps to get p minus 1 pass algorithm. So it's like small trick. Okay? Now let's look at the approximation. Okay? Let ui be the set of uncovered elements before ith pass. Let ui be the number of uncovered elements before ith pass. Then what we know? Just before ith pass, right? Then I can say, look at opt times n by alpha I minus 1 is at least ui. Do you agree to this quantity? Let ui be the number of uncovered elements before ith pass. Okay, so what is the total number of uncovered element before first pass? Is opt times n times u1, which is perfectly fine. How many number of elements are there after second round? Let's try to understand that. Look, what this tells you? How many elements are left in a set in the ith round? This is all that it tells you. It gives you an upper bound on the set size in that ith round. So what is a set size in the first round? Is at most n. So if I take opt times n, that is definitely larger than this. What is in the second round? I know that there is no set which can cover more than root n elements. For example, if I had, depending on what alpha is, but if I took root n, then this tells us that look, I is 2 minus 1, say alpha is n half, for example. Right? Then what does it tells us in the second round? It tells me that look, opt times root n is greater than u1. Sorry, opt times root n is greater than u2, which is correct. Because no set, opt is also a solution to all these uncovered elements, right? And opt's intersection here is how many? No sets can cover more than root n elements. So that is why opt times this is at least ui, okay? And so in ith phase, we add at most how many elements? In ith phase, we add at most mod ui divided by n by alpha I elements, which is less than equal to alpha times opt, right? From here, because look, in each round, so this is the right way of looking at it, right? This is what you get. I mean, I could have also got from here, right? I can take, I divide this, multiply with alpha and divide by this. So this is what it is, right? So this many sets we get. So in total, we add how many sets? We add how many sets? In total, we add p alpha sets. Because this is we add at most these many sets, right? Alpha times opt set in any pass, right? And there are p passes, so you add p alpha sets, right? So you added how much, right? P times n to the power 1 by p sets. That's it. Right? So I have shown you an upper bound of like alpha times opt. In each round, we are never adding more than these times opt sets, right? So if there are p passes, you are totally adding p times opt sets, okay? Opt sets. So approximation ratio is how much? That's it. Okay, so let's stop here.